Hello students, welcome to today's physics lesson. Today's topic is Einstein Photoelectric Equation. By the end of this lesson, you should be able to explain Einstein's interpretation of the photoelectric effect, define work function and threshold frequency, derive Einstein Photoelectric Equation, explain stopping potential, and solve simple problems involving the equation. Remember that according to Planck's quantum theory, electromagnetic radiation is emitted in small packets of energy called quanta. A single packet is called a photon. The energy of one photon is given by E is equal to hf. Here, h is Planck constant and f is the frequency of the radiation. Einstein applied this idea to explain the photoelectric effect. This is Einstein's explanation. When a photon falls on a metal surface, it can transfer its energy to an electron. The electron uses some of this energy to escape from the metal surface. The minimum energy required to remove the electron from the metal surface is called the work function of the metal. The remaining energy becomes the kinetic energy of the emitted electron. Therefore, energy of the photon E is equal to work function W0 plus maximum kinetic energy Ke. Mathematically, E is equal to W0 plus Ke. Hf is equal to W0 plus Ke. Rearranging, Ke is equal to Hf minus W0. This is Einstein Photoelectric Equation. Now, what happens when the photon has just enough energy to remove an electron? The electron will just escape from the metal, but it will have no kinetic energy to move. The frequency of radiation that produces this condition is called the threshold frequency, represented by F0. The threshold frequency is the minimum frequency of the radiation incident on a metal surface required to liberate electrons without giving them any additional kinetic energy. Therefore, work function W0 is equal to Hf0. Substituting this into Einstein equation gives kinetic energy is equal to Hf minus Hf0. This equation tells us that the maximum kinetic energy of the photoelectrons depends on the frequency of the incident radiation. We can determine the maximum kinetic energy experimentally using the stopping potential. A reverse potential difference is applied to prevent the emitted electrons from reaching the collector. The reverse potential is increased until the photocurrent becomes zero. This potential is called the stopping potential, Vs. Stopping potential is the minimum reverse potential difference required to reduce the photocurrent to zero. The maximum kinetic energy is then kinetic energy maximum is equal to electron volts, EVs. Therefore, Einstein equation can also be written as electron volts is equal to Hf minus W, the work function. Or EVS, which is the electron volt, is equal to Hf minus Hf0. Electron volt is defined as the energy gained by an electron when it moves through a potential difference of 1 volt. If the values of maximum kinetic energy are obtained for different frequency of the incident radiation, a graph of this form is obtained. The slope of the graph is Planck constant h. The point where the line crosses the frequency axis gives the threshold frequency F0. If the line is extended to the energy axis, the negative intercept represents the work function W. These experimental results support Einstein's explanation of the photoelectric effect. Example: calculate the frequency of the photon whose energy is required to eject a surface electron with a kinetic energy of 1.97 electron volt if the work function is 1.33 electron volt. 1 electron volt equals 1.6 times 10 to the power of minus 19 joules. H, Planck constant, equals 6.6 times 10 to the power of minus 34 joule seconds. Using Einstein photoelectric equation, Hf is equal to W plus kinetic energy. Therefore, F is equal to W plus kinetic energy divided by H. Substituting the given values, we have F equals 1.33 times 1.6 times 10 to the power of minus 19 plus 1.97 times 1.6 times 10 to the power of minus 19 divided by 6.6 times 10 to the power of minus 34. Simplifying, we have 2.128 times 10 to the power of minus 19 plus 3.152 times 10 to the power of minus 19 divided by 6.6 times 10 to the power of minus 34. Simplifying further, f is equal to 2.128 plus 3.152 in bracket multiplied by 10 to the power of minus 19 divided by 6.6 times 10 to the power of minus 34. F is equal to 5.28 times 10 to the power of minus 19 divided by 6.6 times 10 to the power of minus 34. F is equal to 0.8 times 10 to the power of 15. F is equal to 8.0 times 10 to the power of 14 Hz. Therefore, the frequency of radiation is 8.0 times 10 to the power of 14 Hz. Before we end, remember these four important equations. E equals HF, W equals HF naught, and maximum kinetic energy equals electron volts, EV. Combining them gives electron volts equals HF minus HF naught. Also remember, increasing the frequency increases the maximum kinetic energy of the photoelectrons, while increasing the intensity increases the number of emitted electrons when the frequency is above the threshold frequency. That's all for today's lesson. Keep practicing and you will find photoelectric effect calculation much easier. See you in the next physics lesson. X-rays.